probably ought to start. So welcome to day 2. Today is pretty intense on supernova and neutrino physics. So Tony will continue, and then Christian Ott will follow him. And then this afternoon we'll talk about neutrino flavor transformation, and Wayuan will talk. So a couple of announcements. So we'd like to have a group photo today. And we kind of scheduled for 2:15, so about 15 minutes before the start of the afternoon workshop. And the idea is just meet right around here, and we'll do it on the steps right outside here. Okay. And a second thing is that a number of you, Mike just told me, the number of you have requested that we have a tour of the data center. So how about if we do that tomorrow at about 2 p.m. And again, we'll meet here. So half hour before the afternoon session starts. Okay? Tony.
Great, thanks, George. Today I have a pointer. Okay, so yesterday we laid the groundwork, the fundamental science of core collapse supernovae, the fundamental components. We talked about things like multigroup flux and diffusion and multigroup variable annealing factors, et cetera, just to get all the language squared away. Oops, sorry, forgot to do that. And so now that we've done that, we can get into the business of talking about what's happening, what has happened, and what's happening with specific supernova models. And what I'm going to do today is run through 1D, 2D, and 3D. I will use our models to sort of lay the groundwork, and then I'll talk briefly about what put that in the context of the efforts, ongoing efforts from other groups. And then we'll move on to other things. So beginning with 1D, this was, I think I need to close this door. Helps a little bit. So in 1D, we've been successful in actually solving the general relativistic Boltzmann equation for the neutrino distribution functions for all 3 flavors of neutrinos and their antineutrinos. Obviously, in 1D spherical symmetry, you have 1 spatial dimension. You need 1 angular quadrature, mu, and of course you have energy, neutrino energy, E. So it's really a 3D problem. But nonetheless, we are able to do that, and that's been put in place. And of course, it will tell us a lot, as I'll describe in a second. And it also is important to layer the dimensionality and the physics in the supernova problem in order to ultimately understand what's happening. You need to know what dimensionality contributes, what various components of the physics contribute, ultimately to the explosion dynamics, explosion mechanism. So you see here on the left and on the right results from both Newtonian and general relativistic simulations. The ones on the right, I'll stick with those. This is a full GR hydro, full GR Boltzmann, full Einstein system solve with, of course, all of the detailed microphysics. And what you have here are plots that show the radius versus time of the shock trajectory. And I'm showing this from Liebendorfer et al. 2001, but there's an updated version of this. This was all repeated more recently in 2012 by Eric Lentz, our research faculty member at Oak Ridge and UT. And you see here from 13 to 40 solar masses, the shock trajectory increases with radius and then sinks. So these are all duds, okay? So what this tells us is that because of the implementation of full GR, full Boltzmann, et cetera, modulo effects from neutrino mass, which are not included here, it tells us that neutrinos alone cannot power core collapse supernovae, that they must be aided by other things, other effects. So what are those other effects that are missing? And there are clearly the imposition of spherical symmetry has basically taken out the entire picture I described to you yesterday, neutrino-driven convection, the SASE, all of that is gone. It's no longer there. It cannot aid the neutrino heating in the ways that I described. And clearly that's the first target, right? Let's see if we break spherical symmetry, we go to axisymmetry, and then ultimately to 3D. Let's see how the outcomes change. Now it's, yes, Mike?
You could still build multidimensional physics into a 1D model. You could model
Right.
So is any of that in that?
No. So this is without a phenomenological treatment, for example, of neutron fingers, right? So Jim Wilson, using mixing length theory, put neutron fingers into his simulations, and with neutron fingers he was able to explode stars in spherical symmetry. However, that's really not strictly a spherically symmetric model. I mean, it is and it isn't, but you know what I'm saying? It's introducing non-spherically symmetric physics in a phenomenological way, so I consider that breaking spherical symmetry from a physics standpoint. Okay, and it's really easy to understand, if we go back to this picture, why this fails. So remember that the neutrino luminosities are powered by accretion. So the infalling matter, gains from the gravitational energy, it gains kinetic and internal energy, it slams down on the protoneutron star surface, and that energy is radiated away in neutrinos. So the energy source for the neutrinos, which are powering the explosion, comes from accretion. And in spherical symmetry, once you generate an explosion, you stop the accretion. You cannot have accretion anywhere, otherwise you break spherical symmetry. So once you start the explosion, you stop the fuel that fuels the neutrino luminosities that are generating the explosion. So it's a very precarious place to be. Turns out that, as I mentioned yesterday in the work of Kitawa et al., for 8 to 10 solar mass stars on the lighter end of the massive star range, one can deposit sufficient energy early to generate an explosion and set it in motion. But generally that's not true, and it's not true for that reason. So you have to break spherical symmetry in order to enable simultaneous accretion and explosion. And that's where, and I'll go back all the way to what we showed earlier, that's where this comes in. You see, once you go to 2D, axisymmetry, and ultimately 3D, you allow for simultaneous upflows and downflows. You break spherical symmetry, and you have accretion as well as explosion simultaneously, okay? And so that's what's critical, that's the essential critical piece that's missing in spherical symmetry. All right, so having said that, let's move on to see what happens in 2D. So here on the left, just for reference, I have the spherically symmetric results in the general relativistic case. And on the right, I'm showing the results from our suite of 2D models. And we're using the Chimera code, which I'll give you a slide later that shows all the physics in the Chimera code. But the Chimera code contains all of the physics that I talked about yesterday. And with that code, we've carried out 4 2D models, excuse me. And on the top plot, you have shock radius versus time. And you see here, let's focus on the angle average shock radii, the solid lines, and you have 12, 15, 20, and 25 solar mass models. So these are models that span quite a range in progenitor mass, from 12 to 25. So we're getting up there in terms of massive stars. And you see here, the situation is quite different. In all 4 cases, the shock radius versus time increases. These models all explode. Okay, it's quite different than the situation here. From 13 up to 25, the counterpart span, they're all duds in spherical symmetry. And essentially, these explode because of the presence of neutrino-driven convection and the SASE in conjunction, in concert with the neutrino heating that changes the game. And of course, this is in 2D. We have to reproduce this in 3D as well, and that's ongoing, and I'll discuss that in a moment. Let's look at the explosion energy versus time. That's very telling with regard to what I mentioned earlier yesterday. The time scales here are significant. They're much longer than when Jim was modeling. We're not looking at 300 to 500 milliseconds anymore. we're looking at 1.5 seconds, and in 2 of the cases, and even 3 arguably, the simulation is not nearly finished. So you have here the explosion energy versus time, and let's again look at the 12, 15, 20, and 25 solar mass cases. And in the 12 solar mass case, the red line, the simulation is done in the sense that the explosion energy has basically flattened out, and it's an explosion in the 0.3 beta range, so 0.3 times 10 to the 51 ergs. A beta is a unit of explosion, 10 to the 51 ergs, okay? And so this one we can say is done, and as a result, we can perform all kinds of post-processing analyses on it, as I discussed with colleagues over lunch yesterday. Let's look at the 15. The 15 is almost done. It's beginning to flatten out here. This shows it at 1.2 seconds. It's beginning to flatten out. It needs to go out a little bit farther, but it's leveling off at a much more robust energy of 0.9 to 1 beta. And so that gets into the canonical supernova energy range for the 15 solar mass case, which is, has been for the community sort of the canonical progenitor to use in terms of establishing success and comparing across groups. But if you look at the cases 20 and 25, we have the gold here and the green. You can see that they are very much still developing, and I'll show you that in a different way later. And so they are nowhere near being done, even at 1.4 seconds after bounce. So that's fundamentally different than the situation we had in the past prior to the introduction of the SASE into supernova theory. The SASE, as I'll show you, really has a fundamental impact on the structure of the explosion and on the accretion flows and on sustaining those flows long term to power these explosions over much longer time scales. They basically unfold much more so than sort of happen quickly. One of the things to note too is here with the solid lines, I'm showing the explosion energy, which includes all of the components that should go into such a definition. And there are people have different definitions about what constitutes an explosion. People will say, well, when the shock hits 1,000 kilometers, you have an explosion, et cetera. There are various definitions. For me, I prefer the definition that when the explosion energy becomes positive, I call that the time of onset of explosion. And you see here in the 12 solar mass case, that happens at about 350 milliseconds after bounce. And in the case of the 15, it happens a little later at close to 400. In the case of the 20, at 500 to 550 milliseconds after bounce. And in the case of the 25, at 650 milliseconds after bounce. So these are all, in Jim Wilson's terminology, delayed explosions. These are not early explosions. They're delayed, and the delay is a function of the progenitor mass. And some of them, the more massive cases, are quite delayed. Okay? So this kind of gives you a sense. Things are really quite different than in the past. The timescales are quite different, and that's because largely of the introduction of the SASE. The SASE, the timescale for the development of neutrino-driven convection is typically in the 50 to 100 millisecond range, although that's a function of the progenitor mass. And the timescale for the development of the SASE is typically more like 200 milliseconds. So you really have to run these simulations much longer for the SASE to develop and for the explosion to be set up and then to unfold. It's fundamentally different timescales that we're working with. I want to just complicate the picture for you. Hopefully you can see this. This was the simple picture I kept showing you. And on the right, you have what you're going to see is, and this was a beautiful movie produced by Austin Harris, who's with us. You're going to see two things on top of one another. The neutrino heating, so blue would be cooling and red would be heating. So blue is cooling here and red is heating here, right? So neutrino cooling region, neutrino heating region. And you're also going to see what's called the diagnostic energy, which is just the local energy of a zone, the kinetic, thermal, and gravitational energy of the zone. It doesn't include any binding energy it has to overcome, the overburden, or the nuclear burning energy it will regain as the explosion unfolds. So it just gives you a sense of what mass is possibly ejected here. And you see here, there's your blue, that's your neutrino cooling region, and the red is your neutrino heating region. This is by far, the interface between the two is far from a simple circle. It's a very complex surface, and let me go back, because as we zoom past here, it's a very complex surface, and it's even, oops, I'm going too fast. Here we go. It's a very complex surface, and it even breaks up. It's not simply connected. There are little islands of heating on top of the cooling region. So it's very, very different than the simple picture I showed you earlier. So that was the purpose of showing this. I'll let it run through one more time before moving on to the next slide, which will give you the full dynamics from one of our 2D models, the 15 solar mass model. And you'll get to see how the SASE fundamentally alters the explosion morphology, the accretion structure, and therefore ultimately the timescales. But this is really quite complex, and this is in 2D. So you can see here that we're dealing with a much more complex scenario than is shown simply in this diagram. So we break spherical symmetry in a lot of different ways. Okay, so this is from our 15 solar mass model. I'm going to show you basically the full evolution of the explosion. You see here the shock wave. The top panel shows entropy, which is equivalent to temperature, heat. Red would be hot matter. The bottom shows radial velocity, so you can kind of track the upflows and downflows by looking above and below. So this is the supernova shockwave. You saw the onset of early convective activity, which dies out. Now you see here development of neutrino-driven convection and the SASE on comparable timescales for this progenitor. Okay, we'll let it unfold a little bit longer. This is an outflow. These are inflows. The blue is inflowing material. The red is outflowing material. And you can see what's happening is that because of the imposition of axisymmetry as well, the explosion, of course, preferentially happens along this direction, but of course, at the end, everything goes. And you can see, if I define this to be the equatorial plane, you'll see that the SASE and the explosion morphology that ensues sets up these large, very massive accretion funnels that come down to the protoneutrons, that slam down on the protoneutron star surface and continue to fuel the accretion, continue to fuel the neutrino luminosities, which are in turn generating the explosions. And we follow this out to, this will continue to zoom out to the edge of our grid when our shock finally hits the edge of our grid at 20,000 kilometers.
How many SASE cycles do you have in this model? Because I'm following the oscillations.
Yeah. Yeah, that's a good question, Christian. I don't know precisely how many cycles there are. We know from the modal analysis that the SASE actually is there and operative. I'd say not very many, though.
You guys haven't shown a plot of that. I would be very curious.
Yeah. So that's hitting the outer edge of the grid, and we stop there. So let me go back and talk about the neutrino heating a little bit further in this context. So let's let this go through again, and I want to show you what's happening here, that because the neutrino heating in the heating layer here happens, the neutrino flux falls off as 1 over r squared, and the densities also fall off. So you expect that the dominant neutrino heating will happen very deep in this gain layer, in this heating region. And in fact, you'll see from this analysis that I showed you earlier that in fact happens. What you'll see is a material being heated in a very deep fashion and then gaining energy locally to become totally positive in energy in the sense of summing up the kinetic, thermal, and gravitational. So the neutrino heating is happening very deep down. Here's the shock. So this is the entire gain region here, but the heating is happening in very, very deep in the gain region. And then you'll see what happens is material that is heated deep down becomes buoyant and moves outward. And as it moves outward, its energy continues to change and ultimately becomes positive. So it's very important to note that the heating is happening very deeply, and that continues to supply energy into the system, which then is transported outward. And of course, anything that's green here has a prayer of being ejected, but it's not guaranteed to be ejected because that green doesn't take into consideration the work that has to be done on all of the star outside of it. But this is a good indication that this material will, in fact, likely be ejected in this scenario. Okay. So that's one of the things that is always important to do. As you know, science is about, it's very important for the supernova groups at the end of the day to agree and all sort of be on the same page. I mean, our understanding depends on that. But the most important thing is that the supernova groups have to reproduce observations. We answer to Mother Nature first and then to each other second. And we've never been able to do this in the past. I mean, it's really a gift to be able to get results and to be able to compare those results with observations. So on the left, I have explosion energy versus progenitor mass, and the crosses indicate the observations, and of course the error bars are large, but that's what we have to work with. And we have here our explosion energies. There's our 12, there's our 15, there's our 20, and there's our 25. The arrows indicate the magnitude of the arrow indicates the rate of change of the explosion energy in the model. So in the 12 solar mass case, as I showed you, the explosion energy leveled off. So the E dot is small, if negligible. So this is essentially finished. The 15 still has an E dot and will still move up in this plot as we carry the simulation out further, but it's not moving rapidly. But very clearly, when you get to 20 and 25, you see the E dot here is really non-trivial, very significant. And so these are not anywhere near being done. And so these have to be continued. But on average, I would say that these explosion energies, while robust, are on the low side in relation to observations. And obviously, that's something that hopefully in 3D will change, but we'll have to perform 3D to know. But nonetheless, we are certainly in the ballpark, which is very encouraging. If I look at the nickel 56 mass that's produced versus progenitor mass, this is basically the mass of the material that's ejected. And in this particular instance, our predictions are excellent. They're much more in sync with the observations. And so, that's something that will have to be better understood and explored, especially in 3D. But nonetheless, these are 8 different observables that are fairly well pinned down by the models, which is very, very encouraging. And then finally, I'll show you and I'm running off the grid a little bit, the protoneutron star mass versus time after bounce. So we know that we have to produce neutron stars, black holes in some cases, neutron stars in these supernovae. And we know from observations that neutron star masses are clustered in the range around 1.4 solar mass. This is gravitational mass. Our predicted baryonic masses are between 1.5 and 1.9, and so the gravitational mass in all 4 cases would be lower. We should really plot that as well. And so our gravitational masses will in fact be in the range shown here from observations. So once again, the 4 predictions for the 4 neutron star masses are in sync with observations. And then here too, we're predicting, we know from observations of pulsars that neutron stars are given kicks in these supernova explosions, they're not spherically symmetric explosions, so there's a net momentum deposition to the neutron star, and the kick velocities from pulsars have a bimodal distribution, peaked around 0 and around 1,000 with a mean of about 450 kilometers per second. So generally, you need to be able to produce neutron star kicks in the 100 to 1,000 kilometers per second range. And in fact, that's what we are finding. So the 12 is about done, and that's a kick velocity just above 100 kilometers per second. The 15 is not quite finished. That's also in that range. But clearly, the 20 and 25 solar mass cases have to be evolved further before we know what the kick velocities are there. So we're talking about a lot of observations here, a lot of numbers, to be able to predict and to predict accurately. And so these are very encouraging results from the models that suggest that we're on a good track here. But obviously, Mother Nature is not 2D, and in fact, it's puzzling how the results are so commensurate with observations based on the 2D simulations. That's an interesting question. So we just have to carry this out in 3D, which we're now doing. And of course, I showed you 4 2D models. We run them, easily run 4 at a clip. We have another 8 ongoing now. So we have the ability to run a lot of 2D models, but 3D models, as I'll show you, are far more difficult, far more expensive. And so I'm going to show you the results of one ongoing 3D model that's running on Titan. And what you'll see here, I'm going to show you, we've gotten to 330 milliseconds after bounce. On the left, you have an equatorial slice, and on the right, you have the full volume rendering. This was produced by Bronson, who's with us today. This one, these movies are not all up to date, so this one will only run to about 180 milliseconds after bounce. This one will run to 300 milliseconds after bounce. And then I have some snapshots for you that I got last night from Eric Lentz that take us all the way to 330. But you can see the development here of neutrino-driven convection, and then there is some mild SASE activity ongoing in here. And you can see that we've broken symmetries. There are no imposed symmetries here. This is not symmetric. It's not spherically symmetric. It's not axisymmetric. And on the right, you have the full rendering to 300. And here, later on in the simulation, you clearly see some of the bipolar structure, and even as if we were watching earlier, and I'll go back and do that again just because it's important to talk about. You'll see, this is fun to watch because initially you're literally watching the star boil. So this is largely neutrino-driven convection here. This is the 15 solar mass case. And you're watching the star boil before it explodes. And toward the end of this run, close to 300 milliseconds, on a time scale larger than 200 milliseconds, as I indicated earlier, you'll see some of the early SASE activity, both the L=1 mode, but also the M=1, the spiral mode, which is not admitted in two-dimensional simulations. And while this develops, and we can just watch it here for a second, you see obviously there's an elongation here that happens, and near the end you'll see some of the flows beginning to wrap around from left to right here on the bottom. So there's clearly M=1 activity as well as L=1 activity ongoing here. Just to give you a sense of scale, this is running on about 65,000 cores on the Titan supercomputer at Oak Ridge. We get a post-bounce second takes 35 weeks of runtime, of actual runtime. And so we estimate that for a post-bounce second in 3D, we're going to consume approximately 100 million processor hours. And we have to run clearly, as I'll show you, the 3D is even more delayed than the 2D. We're going to have to run for more than 1.5 seconds. So these are, because of the physics that's in them and the time scales over which these have to be run, and the fact that it's now 3D, these are extremely, extremely expensive runs. But the problem is extremely important to solve. So It's very much worth our effort and the cycles on the machine. Let me give you some snapshots of where we are now. This is 330 milliseconds after bounce, and I only have the snapshots from this period beyond the movie, the movie I showed you earlier. And you can see here, this is 1D versus 2D versus 3D. 1D is red, so this is all for the 15 solar mass case. So 1D does not explode. 2D, as I showed you, does explode. And it looks like 3D is also going to explode, which is very encouraging. I mean, we're very excited about that. But of course, it may explode, and the energetics may be poor. You know, we won't be able to speak about quantitative aspects of the explosion until, you know, much farther into the academic year. But nonetheless, this is really a very important trend. I don't think this is a temporally local trend, and so we just have to continue on and see what we get. This is a snapshot of where we are. This is the surface of the shock, and you can see it's a rather complex surface. And these are two different slices through the 3D volume, one equatorial and one polar. And you can see that there is no symmetry imposed here. That one slice, they look similar in some respects, but they are clearly different in important respects. So this is very much a 3D problem. Wendell, you had a question?
Oh, it was just in reference to the m=1 mode.
Yeah.
Is that spontaneous, or is that due to some initial angular momentum?
No, it's spontaneous. If you start with a non-rotating progenitor, so total angular momentum 0 in the model, the m=1 SASE mode will be triggered. It is, in fact, you can do a linear stability analysis and show that m=1 and l=1 are both unstable. I gave the references in the slide on the SASE. So if you go to those references, you see that they are, in fact, unstable modes. They will both kick in. And in fact, what we found was, in sort of numerical experiments, we found that the m=1 mode can actually, it may be that the pulsars are spun up by the m=1 mode in supernovae. And what happens is, even with total angular momentum, the m=1 mode causes a rotating flow beneath the shock, and deeper down there's a counter-rotating flow. So the total angular momentum remains 0, but the differential angular momentum is quite significant. And the inner angular momentum accretes down onto the protoneutron star and can deposit that angular momentum, and it's possible that that's how pulsars are spun up. 3D simulations like this have to be performed by us and by others before we know that's in fact the case, but it's possible that that's how it happens. So it's really remarkable that you can start with, you can have total 0 angular momentum in the system and wind up with a pulsar spinning at 50 milliseconds. So that's the prediction we made, that was in the observable range. And that's the power of the SASE and of these modes that are not operative in spherical symmetry or in 2D. 3D opens up new doors. Elizabeth, you had a question?
What code are the 3D simulations in?
Everything is done with Chimera. These are all from the Chimera code, and I have a slide on that later that kind of shows you everything that's in the Chimera code. So they're all done with the Chimera code. So, and in fact, here's the slide. I won't bore you with this, but for those, just for reference sake, it includes all of the physics that we discussed earlier, but it includes some of the physics in an approximate way, and let me discuss the most important, because it's, yeah. This is a polar grid, yes.
So can you do advection across the pole?
Can we do advection across the pole? Yes.
Because it's a singularity.
Right, right. So this is the grid that's being used here is a constant mu grid, and then we refine, because constant mu, constant cosine theta, will give you coarser zoning along the pole and finer zoning down toward the equator. But we compensate for that by refining near the pole during the simulation as we go. So, and we've been able to do that. We can talk more about that offline. Maybe Bronson, you have a comment on that, on the details on that?
currently the 3D, in fact, we're not advancing across the pole. We're essentially freezing the pole to prevent just that problem. Because the new grid gets rid of the sort of the transverse Coulomb condition problem at the pole, but you still have the problem going straight through.
Right.
The true singularity rather than just numerical. So actually cut that down. We changed the size of that region that we exclude.
Right.
We don't see any dynamical impact.
Right.
But yeah, it's
Right.
it's not without its
I
problems.
mean, that could impose asymmetry.
It couldn't.
Yeah.
We don't see
Right.
waves propagating from that, but based on how many zones we freeze, for example, at the pole. So I wouldn't say we were sure, but we're fairly sanguine.
Yeah. So it's very important. I made a big deal yesterday about the neutrino sector and the need for multifrequency, full spectral treatment, and what multigroup flux-emitted diffusion is, what multigroup variable radiation factor, radiation tensor is, and all of that. It's very important for you to understand where the field sits in regard to that, whether you're working on this problem or thinking about working on this problem or working on other problems and need to interpret what's happening in this field. So our simulations deploy what is known as the ray-by-ray approximation, okay? It's very important to understand that in terms of interpreting our results, and then I'll put it into the context of others. So in the ray-by-ray approximation, instead of solving, say, let's just keep it simple, we're looking at a 2D plane here, so in 2 dimensions. Instead of solving one 2-dimensional multi-frequency transport problem, we solve n spherically symmetric transport problems. And each n is the number of angular zones. Okay, so say that's one angular zone, that's another angular zone, all right? Now, the advantage of that, of course, is that if you're doing ray by ray, and you're solving, therefore, n spherically symmetric problems, you can use the very sophisticated transport codes from 1D in the context of 2D and 3D simulations. And these very sophisticated transport codes have all the physics in them, modulo this assumption. Now, how good is the ray-by-ray approximation? How good is it, or how good might we expect it to be? Well, let me take an artificial situation where I have spherical symmetry initially, and I break it, and I put a hot spot right there on the surface. Okay? If I look, the heating at this point is determined by the entire surface subtended by this cone, this backward causal cone. And if in a spherically symmetric model, the surface will be assumed to be the temperature of the hot spot at the base of this, at the center of this cone. Okay, so it's going to overestimate the heating, the neutrino heating there. Now, if I flip over to the next zone, the heating here is determined by this entire subtended surface. But here I'm going to assume that the heating here is determined by material spread across the surface at this temperature, cooler temperature. And that's going to underestimate the heating here because this hot spot also contributes to the heating here. Okay? So ray by ray will in fact accentuate angular differences. It will overestimate and underestimate heating as you go around an angle. However, the real question is whether the hot spot stays there through the course of the simulation. And this is the extreme case where I'm assuming the hot spot remains there. But as you saw, when those accretion plumes hit the protoneutron star surface, those hot spots that are generated, that material spreads across the surface rather rapidly. So ray by ray is exact in spherical symmetry. It's exact. And so the more spherical the source of neutrinos, the better ray by ray will be. Precisely how good it is will require a comparison of a same code that uses ray by ray and doesn't. And that can't be, we can't do that yet, and nobody can do that yet, and eventually we'll have to do that. But in the meantime, ray by ray could be quite good and affords us the ability to put a lot of physics into the models. And especially in 3D, I showed you that we're going to spend 100 million processor hours using the ray-by-ray approximation. So with all that physics in fully 3D, I mean, you can imagine the computational cost. So it's very important to remember this. And in fact, in interpreting what's happening across groups, really there are two lines of attack that are ongoing now. You have those that deploy ray-by-ray and those that don't. And essentially what's happening is right now the ones that do have GR in them, full neutrino weak interactions, which we'll discuss, so the full physics, but the ray-by-ray assumption, which in a way also reduces, it cuts out part of the physics, right? It cuts out part of the transport physics. But the rest of the physics is in there. And then you have the models that are out there now that have fully 2D, 3D transport, are Newtonian and have a reduced set of weak interactions. And as I'll describe to you as we get into the microphysics, one of the reasons for doing this is that the weak interactions enter the collision term of the Boltzmann equation or the moment equations, and they are what determines this to be an exascale problem. So approximating the weak interactions has a very practical motivation. If you approximate the weak interactions, you make the problem computationally less expensive. But the problem is that you can't physically approximate the weak interactions in that way because it's just physically not correct. So at the end of the day, what has to happen in the community is that these have to merge, right? These have to merge. And that is happening and will happen. But in the meantime, ray-by-ray is a very, very effective approach. We have these other approaches in parallel. And if I look at the state of the art in the literature now, the ray-by-ray practitioners are in these groups, and I think I've listed the order in which they first appeared in the literature, and the non-ray-by-ray are in these groups. We at Oak Ridge have a non-ray-by-ray effort as well, the development of the Genesis code, which is our next generation supernova code, which will be full GR with multigroup variable Eddington tensor approach. So, but I haven't listed us here, even though we are working on this, just because we've not published any supernova models with it, whereas these groups have, okay? So I just want, this is a technical detail, but it's very important for you all, as students, as postdocs, as the next generation in our field, to understand what's happening, what the state of the art is in core collapse supernova modeling today, and why, because it's so difficult and expensive. What I've done here too, I've given you two slides, again in the spirit of, like I did yesterday, in the spirit of giving you references that you can, handles into the literature, where you can get other perspectives, more detail, etc. And I gave you supernova theory milestones yesterday, and today I'm going to give you some milestones in the transport sector. So, and it gives you some historical perspective on the first deployment of 1D multi-group flux emitted diffusion. So this is multi-frequency in 1D, Boltzmann in 1D, multi-frequency in 2D, Boltzmann in 2D, and in 3D. Christian's paper on 2D Boltzmann is a masterpiece. I encourage everybody to look at that. And now the Japanese group, Sumiyoshi-san and Yamada-san, are both also pushing this in 3D. But obviously, all of the physics is not yet in these models, but these are very, very important and large steps forward toward better supernova models down the road. Just to give you an even more fun view at this, remember I mentioned that this is a phase space problem, not a spatial problem. So it's good to really look at this dimensionality as a phase space dimensionality. So here, going all the way back, I'll just for completeness, these are the first numerical simulations performed, Colgate and White, Arnett, Wilson, and Wilson in '74. These are the very early runs, so I just want you to have those as well. But if I really start with contemporary supernova theory with Wilson '85, this was a 1+1D model. So one spatial dimension, spherical symmetry, and multi-frequency, 1+1D model. Harant et al. Came along with the first 2D models, so 2 spatial dimensions. So this went from 2D to 2D. We performed the first 3D models, so this is 1 spatial dimension radius, and now you have a direction, cosine, and an energy for the Boltzmann case. So these are 3D. Chris Fryer and his collaborator Warren produced the first 3D models, so spatially 3D, but integrated in neutrino angles and energy, so a gray treatment. Then you get up to now where we're doing 2 spatial dimensions plus multi-frequency, so 3D models. And then you get to models that I showed you and the ones from the Max Planck group that are 3 spatial dimensions plus multi-frequency, so 3 plus 1. So we've gone from 2D to 3D to 4D. And then finally here, again in Ott et al. And Brandt et al., these are the early attempts at 2 plus 3D. So 2 spatial dimensions, axisymmetry, plus 3, so it's Boltzmann implementation, so it's 2 angles and 1 energy. So it's a 5-dimensional model. So I wanted you to see this because when you really tabulate the dimensionality fully as phase-space dimensionality, you realize how hard this is and how big of a deal it is when you have 5-dimensional, ongoing 5-dimensional simulations. People talk about 3D as if it's the end all, but really we're in 5D and ultimately we'll need to be in 6D, right? Plus time. So I wanted you to have those references as well. So the microphysics. So George, I am, according to my clock, I've gone in 45 minutes. Would you like me to continue a bit longer and then we'll stop for questions?
Whatever you would like to do. If you could stop for questions now and pick it up later, this is a convenient stopping point.
Okay, well, how about I stop for questions now since I won't have a whole lot of time to delve into this today, and then we can figure out what to do about that. Okay.
That sounds perfectly good.
Okay. Any questions from anybody at this point?
Why you?
So for a 3D simulation, how can the neutron star get a pulsar kick? Is that from the Saucy mode, the L equals 1 mode?
Yeah, so you have accretion onto the protoneutron star. And if the accretion is not spherically symmetric, there will be a net, whether it's in axisymmetry or in 3D, there will be a net, because of the convective modes and the Saucy modes, there will be a net linear momentum imposed to the central object.
So that the swashing up and down,
Yeah.
That's not really symmetric.
Right. Right. Axisymmetry, in axisymmetry, the symmetry is about this axis, not that axis. I should point to you, right? So if I look at a 2D slice and I assume axisymmetry, I'm assuming it's symmetric about this axis as I rotate it, but not about this axis.
Right, but there's oscillation.
Right.
That oscillation amplitude is not symmetric.
Right. Right. And in 3D, it's still there. And of course, you have m=1 modes as well. And so the net effect of neutrino-driven convection and the Saucy in 3D will impart some net linear momentum to the object.
Early this year, I also talked with the student of Young. So he mentioned that today with both solid-state neutrino transport and the 3D, spatial 3D, the supernova model doesn't really explode. Can you comment on that?
Whose student was this?
Thomas Young.
Tomas, yeah. So I'm glad you asked that question. So let me step back from that question and answer a broader question that's also very important for this community to understand. One cannot compare across supernova groups straight away. In fact, you can't, period, because some of the simulations, 2D, 3D, are Newtonian and some are have GR, for example. There are other, some have full weak interaction physics and some don't. So we cannot compare across the board, and some of my colleagues want to do that, and it's just not scientifically sound to do that, okay? number one. Number two, the Max Planck group and the Oak Ridge group can in fact compare. That's an apples to apples comparison, not an apples to oranges comparison, because all of the same physics is in the models, and the approaches are actually rather similar, with the ray by ray and all that. Why they don't explode and they do explode. Well, in 3D, the most recent results that they've shown from 3D, which go to...
I just saw Tomas talk about this last week, and he had a curve that looked very similar to what you showed me with the effect of 3D.
Yeah. So, that's good news, because what's published in Henke et al. In literature shows the shock trajectory actually going down, not exploding. Now, of course, it does not look optimistic, but of course, as I mentioned, you have to carry these simulations much farther out before you can make final conclusions, and that's not been done by Max Planck. No one has run for 1.4 seconds after bounce, and these explosions are still developing. So even if you do explode, and you claim that the explosion energy is weak, that's a very dangerous thing to do, because particularly for more massive progenitors, you have to evolve much longer before you can make conclusions about the explosions. Now, going back to the original question on 3D, ours look to explode. Theirs, from what I saw, it may have changed or not, and we have to come to understand why that is, but, and we don't know, but at the end of the day, we have to compare to observations, and our 2D results compare well with observations. Theirs do not. And in 3D, we haven't, of course, compared to observations yet, nor have they. Okay? So that has to be understood, why the quantitative differences exist between Oak Ridge and Max Planck. But at the end of the day, answering to Mother Nature is what we're supposed to do, right? Not answering to what Max Planck group sees.
Alex?
The different boxes, I'm sorry. Oh yeah, the CPU time is dominated by the transport.
So if you were to do ray by ray on top of it, would that kill it, or, sorry, not ray by ray, but more beyond ray by ray, more accurate ray tracing, would that kill it or not?
Beyond ray by ray, you mean to go fully 3D?
Or some intermediate stuff. I mean, if you were to spend most of your time on somewhere else, you could increase the time spent on this.
Alex, would you mind repeating your question?
Yeah, sure.
Can you hear me now?
I'd like to be the technical.
So the first question is, the code has different segments, different parts, transport versus hydro versus other things, and depending on what the breakdown of time is now, how expensive would it be to go from, you could do ray by ray in the diffusion regime, but could do better ray tracing outside, for example. How much would that be of the overall budget?
I don't have a quantitative answer. I know that if we were to go to full 3D transport, multi-frequency with all this physics, obviously the 100 million processor hour runtime CPU usage would be much, much higher. But of course, but it's complicated to talk about, because what you're going to do in a situation like that is you're going to strong scale over a bigger fraction of the machine, or over a bigger machine. For example, the next generation machine at Oak Ridge in 3 years will be a 200 petaflop machine rather than a 30 petaflop machine. So as the machines grow in size and you strong scale over more of them, it's possible to consider these simulations. The run times are still reasonable, but of course the CPU, the processor hour costs are going to go up.
That's also machine dependent.
But the total processor hours available also goes up.
With Titan, you could do ray tracing on GPUs, and that would be
Yeah.
quite effective.
Yeah.
And the second question is on the physics.
Alex, you're asking very good questions, but very complex questions that can't be answered on the fly. So.
But I mean, you just made it interesting.
Good.
And the second is on the physics of turbulence. So in 3D, turbulence tends to shred and cascade.
Yes.
So do you see
Yes.
large-scale features persistent there?
Excellent question. Okay, so I didn't show that, and that's actually a worry of mine, and we'll have to see how 3D plays out, although so far so good. The SASE is a global long wavelength mode. And in 3D, in fact, we mentioned Wendell earlier, the m=1 mode leads to significant shear in the system. And the shear leads to Kelvin-Helmholtz instabilities, and you develop turbulence right in those regions. And in fact, we see that in the models. A detailed analysis was done by Eirik Endeva in our group and published a few years back on that. And actually, you know, it's real turbulence. It's Kolmogorov scaling turbulence. Now, in 3D, the turbulence cascades to smaller scales, so it will sap energy in long wavelength modes and move that energy down to smaller scales. In 2D, it's the other way around, okay? So I call it a David and Goliath battle, right? Long versus short wavelengths, and who will win out remains to be determined, but it is a concern of mine. I know it makes you happy because, you know, with all the turbulence and things like that, it makes it more interesting for neutrino mixing, but it gives me headaches.
It doesn't make it more interesting for neutrino mixing, it just makes neutrino mixing harder to deal with. Maybe more interesting for him.
He seems pleased when I talk about it.
How do you test a code like this? Like, there aren't analytic solutions that have neutrino transport in them.
Great question. I love that question because at the end of the day, you know, you can test modules, right? You can run tests that have analytic solutions. You can compare to, you know, laboratory experiment, etc. But at the end of the day, when you pull all of this multiphysics together, the only thing you can do is test against observations. So, you know, I mean, I showed our predictions against observations of explosion energies, observations of nickel mass, observations of neutron star masses, observations of neutron star kicks for each of the cases. So that's 16 different observables. That to me is how, you know, ultimately these are validated. I think one is kidding oneself. I mean, certainly it's good to develop each module as best as you can, following best practices. I'm not suggesting anything different. But one is naive to think that if you then assemble it all, that, you know, you're carrying forward, you know, everything that you had in each individual case, and you're not. And you have to compare against observations.
So, Tony, I agree with you that you want to compare with observations, but now I'm in a very observation-heavy institution. I actually have nights at Keck, and I understand a little more about observations now than I did before. And the systematics of observations will just completely wipe you out. There's no way you can predict the nickel mass and then take a supernova observation that has some nickel mass estimate. It's just way off by factors of 2, 3, 4, 5. So that's not the way I think we'll be able to, for a distant supernova. Galactic supernova, different thing. So I think the galactic supernova is what really will get us this, because we'll have neutrinos, we'll have gravitational waves, we'll have photons, we'll have nucleosynthesis. That's where we're going to go calibrate. I don't think we can do that with a distant supernova.
Well, but I don't take it, I don't disagree with you, but I don't take it as far as you do. You're not suggesting this, but we have to work with the observations that we have, you know, the best observations that we have. And it's the fact of the matter is that you can put up results from a computation and put up the observations, and you can see that there is general agreement there, despite the systematics that you indicate. I agree with you about a galactic supernova. May we get one in about 5 or so years when all of our models are sophisticated enough to be able to reap the full benefits of that.
I think this is a great place to transition to the next.
Okay.
You know, we're certainly going to need a liquid argon detector of some kind. Maybe we can add that on to Keck. I don't know.